Hey there everyone, all the techies and data enthusiasts there. So guys, welcome back to video 7 of our Transformers series, and in this particular video we are going to discuss about masked multi-head attention. What? Previously we discussed about encoders, right? So what happened to decoders? Why are you entering into this? Okay, so guys, for encoders, right, you need to understand about multi-head attention, layer normalization, adds and norms, and also feed-forward neural network that I have explained before encoder itself. But to understand decoders, right, it is very important to understand about masked multi-head attention as well. So that's the reason in today's video we'll discuss about masked multi-head attention, and in our video 8 we'll discuss about decoders. Okay, so guys, now let's get started. Before that, if you have not subscribed the channel, do subscribe the channel and on the bell notification. Make sure to follow me on LinkedIn for latest updates related to content, and if you have any questions, feel free to ask me on LinkedIn. Okay guys, now let's get started. So guys, what is masked multi-head attention in decoders? So in this notebook, we'll explore for masked multi-head attention mechanism in the Transformers decoders, and we'll understand its step-by-step approach. So you can see here there is an example as well. Start, the cat sat on the mat. Okay, so this is the example input sequence. So here what is a note, right? We have already understood about encoders and how the encoder output will be served to decoder, that we'll explore in our next notebook. But now we will focus on mainly understanding the objective of this masked multi-head attention and how important it is for decoders. Okay, so first one, input sequence. The input of masked multi-head attention layer consists of the targeted sequence, which should start with start, and the token includes previously generated tokens as well as proceeded. For example, you can see here, so input sequence, it should always start with start. So whatever input you are going to give, right, that will start with start keyword in front, and then it will complete the sentence, and even there will be coming the end at last. So that I'll explain you. And step 2, so compute the QKV vectors. So those who don't know what is QKV, I have explained that previously itself, so you can go and have a look on it. It's a very important concept which is helpful for us to calculate the self-attention scores or multi-head attention scores. So where this is the QKV, and you have the input embeddings Q, WQ, WK and WV. Okay, so I have explained that clearly in self-attention, which is video 4. You can go and watch about it to understand about this formula in detail, and it's working. Okay, the video link will be in this video description. You can have a look on it. And here is a diagrammatical representation which we have done. Input sequence, which will start. So we have to include start at first. The cat sat on the mat, and you will send it to weights, send those weight metrics for QKV, which is query, key and vector. And finally, you will get them in this format. Q, the Q cat, which is nothing but these all are the attention scores, self-attention scores of Q, K and V. Okay. And here you can see here. Step 3, attention score calculation. The attention scores are calculated using the dot product of Q and K. The attention score indicates how much focus each token should have on the others in the sequence. So you have the attention scores here, Q comma K, that is equals to Q multiplied by K by T. This is your formula. And here you have the diagrammatical explanation about it. So in this entire Transformer series, right, we are mainly focusing on you guys to understand it with the graphical representation. So that's the reason we have created images. So it took a lot of time to create this, but we have created them in detail so that you guys should never lack in understanding these concepts. Okay. And this notebook which you are seeing, you will get this notebook link in this video description. You can go and have a look on it. Not only this, all the notebooks links you will be having there. You can go refer, read it and keep it for your future references. Okay. So here is your query score and key score and the dot product of it. Then we will get the attention score of each word. Okay. So here, for example, the attention score you can see here, start 1.0, 0.8, 0.5. This is just an example. For each word, there will be a different attention scores. Okay. So it depends on the calculation only. You can see here. Then apply masking. So apply masking mechanism to ensure that each token can only attend to itself and the token that precedes in the sequence. This is done by setting up the attention scores for future tokens to navigate infinity or a very large negative numbers. Sorry, to negativate a negative infinity or very large number of negative infinites. Okay, so the mask score is equals to attention score plus mask. Okay, here you can see here attention score of each word. So here we got the attention score of each word after dot product. So this diagram is continuation. After that, what we do, we mask them. We mask it with attention score of each word. Then finally we get masked score of each word. You can see here this is the masked score. So this infinity symbol represents the masked score of each word. Okay, we do this masking, attention masking, and then we start with softmax. After that, the step 5 is to softmax to get the attention weights. The attention weights are computed by applying the softmax function to this, and you can see here attention weights is equals to softmax of masked scores. So once we perform that, then we get attention weights for each word, and here is an attention weights of it. Okay, these are just examples of this particular word, so it might vary. And finally, compute context vectors. So the context vector of each token is computed as a weighted sum of the value vector based on the attention weights. These context vectors capture the relevant information from the previous token to the target sequence. So here you have sigma attention weights dot v. This is the context vector, and the graphical representation attention weights and value. For this again we take out the dot product and dot product of v. Here in this formula it represents, you can see here. So attention weights whatever we get, dot product and v values. So both attention weights and values which we have extracted previously here, right? Here we have taken the values. If you remember, here we have taken the values as well. We only took the attention score of q and k, not v, that is values. So that we are using here in our step 6. So in our step 6 here we get it, and that dot product again we multiply with sigma. Then we finally get the context vector of each word. Okay. Then here you can see a context vector 0.8 start into 0.2 the. So what here it is doing, it is taking the next context, start the cat, which is nothing but 0.8 is the score of v start, value start, 0.2 is score of the. So it is continuous prediction is going on here. The cat sat on the mat, okay, with score and multiplied by that particular word, value word, plus. So finally we get the output as masked one. You can see here start output is C start, C the, C cat sat on the mat, C, okay, on mat. So this is how we get the final masked attention, you can say. Wait, let me just show an image as well. Okay, see this image. So once we get that, right, then you will have like the start, the cat sat on the mat, and this is the end. So what we do is we add the start keyword at first and the end keyword at the end, so the model can understand, okay, this sentence complete at here. So to understand this in detail, right, we will be discussing in our next video, which is decoder part of transformers. So we will understand all this in clear. I hope until here you understood in clear. So the conclusion is very simple. So this masked multi-head attention, it will not do anything. Whatever you got output from encoder, that will be sent to again decoder as an input after masking it. So we perform the masked multi-head attention for it. We take out the QKV of it and we do dot product multiplication, and finally we mask it out with the outputs whatever we get, and we send the masked outputs to decoder. Then decoder will decode it and the final generation will continue, like generating the output. Okay. So I hope you all know that generation is, I mean that encoder is nothing but it is for understanding whatever inputs we give, right? It understands it and it creates. But generator generates this. The example of this both is separate is, if you want only encoders to be used in your project, you can use BERT. You have a BERT model, so you can use it. So the GPT models which you are having, right, this chat GPT and all those models are decoder based model. They have the capability to generate based on the input, but encoder has the capability to understand the sequence properly. Combination of this both is called encoder decoder, is called transformers architecture. You might get in doubt what decoder is separate and encoder is separate. So encoder, stacking of encoder you get BERT, and stacking of decoder you get GPT. Where is the combination, combining this both? Are there any models? You might have a doubt on it. Obviously there are models. So there is a model called BIRD, and also there is a model called T5, which is combination of this both encoder decoder, or you can say T5 is combination of transformers architecture directly. Okay. Okay, guys, I hope you all understood clearly about masked multi-head attention. It's not a big deal. If you have understood the conclusion also, it's enough. And if you see these images and if you read this blog, you will understand properly. Make sure to check out this particular blog and do like, share and subscribe the channel. Meet you all in the next video. Bye-bye.